ozone depletion is closely linked to free radical substitution, and the mechanism is very, very similar. So depletion of the ozone layer and the hole in the ozone layer was a massive thing in the 70s and 80s, and all the countries came together, worked together with the Montreal Protocol, and they've solved a massive environmental issue, which is, in the modern world where we're now caring so much about climate change, going back and look at how we work together in the Montreal Protocol to solve the hole in the ozone layer is a really nice thing to do. So, CFCs, chlorofluorocarbons, are just molecules which contain fluorine, carbon, and chlorine. And we're going to start with a really simple one. Chlorotrifluoromethane. Now, in free radical substitution, we always had an initiation step where we generated a free radical. We're going to do exactly the same here. So we're going to need some UV light, and it's going to break one of those bonds. You'll be expected to be able to predict which of the bonds it's going to break. You've only got two choices: a carbon-fluorine bond or a carbon-chlorine bond. You need to use your knowledge of atomic size to be able to predict this. So fluorine is a really small atom. Chlorine is a much bigger atom because it's got an extra shell. Just think about your experience in life. If you've got, let's say, a pencil in front of you and it's a really short pencil, is that easy to snap? Not really. If you've got a long pencil, is that easy to snap? It's a lot easier than the short one. Whenever anything's longer, it tends to be easier to break. So we're going to break the carbon-chlorine bond because that's the one that's easiest to break because it's a longer bond. So let's get our UV light and break that carbon-chlorine bond. Now, where do you get a lot of UV light? Up in the ozone layer. Why do we not have a lot of UV light on the surface of the Earth? Because the ozone layer stops the UV light getting down. Now, as soon as we go above the ozone layer, or into the ozone layer, if any of these chlorofluorocarbons, CFCs, can get up there, this process is going to happen. And we're going to look at why this process is really bad. So, what we've formed here is a CF3 radical and a Cl radical. And remember, the initiation step always starts off with a normal molecule with no charge and produces two radicals. The dot goes on the carbon because that's where the unpaired electron is. So this is where it starts looking sort of similar to free radical substitution. Although one thing I will actually quickly just mention, when we started off with something like Cl2 and formed two Cl radicals, that was called homolytic fission because we broke up the Cl2 into two identical radicals. This, we've broken up our initial molecule into two different radicals, so we're going to call it heterolytic fission. Because we're forming two different species. Okay, so the propagation step. We're going to ignore the CF3 radical. That doesn't really do much in our process. But we are going to certainly concentrate on this Cl radical. So a chlorine radical is really, really reactive. And the ozone in the ozone layer is O3. And when we did normal free radical substitution, we looked at how the radical could break a covalent bond. And that's exactly what it's going to do here. It's going to break one of the oxygen-oxygen bonds. And one of the oxygens is going to go over to the Cl. However, when the oxygen goes over to the Cl, it forms a ClO radical. And the two oxygens left over are O2. So O2 is obviously really, really stable. And that's why the other oxygen goes all the way over with the chlorine radical to produce the ClO radical. In free radical substitution, in the second propagation step, the radical from the first step came down into the second step. Same thing's going to happen here. So we've got this ClO radical. And what this ClO radical is going to react with is another ozone molecule. And again, it's going to break open the oxygen-oxygen bonds. And we're going to produce... We're going to break open the oxygen-oxygen bonds, and then the oxygen from the ClO is going to join as well. We can't have O4, that's not a stable molecule, but we can produce 2 oxygen molecules. And what we're left here with is a Cl radical. So the Cl radical in this reaction acts as a catalyst. So the Cl produced in the initiation step, that's going to be a catalyst to break down ozone into oxygen. And because that Cl keeps on getting reproduced, so it can be used again in the first one, it can keep one Cl radical, can keep breaking down endless ozone molecules into oxygen, which we don't want, because ozone is what protects the Earth's surface from UV rays. So the only way we can really stop this reaction happening is to get rid of the Cl radical. And we get rid of the Cl radical with a termination step. And that is Cl radical plus another Cl radical will produce a Cl2 molecule. That's the best we can hope for, and that's the way we're going to end this breakdown of ozone. So if we're looking at what's happening to the oxygen, we've got an ozone in the first propagation step. We have another ozone in the second propagation step. So we're going to have 2 ozone molecules. And what's produced is going to be 1 O2 molecule in the first propagation step, 2 in the second propagation step. So 2 ozone molecules are going to be broken down into 3 O2 molecules by a single Cl radical. So a single Cl radical can quickly deplete the ozone layer in O3 molecules by producing O2 molecules. And it's a lot more difficult to make O3 molecules again.